Hello and welcome to Beamer Folk. I'd like to tell you a story about a problem that caused the company quite a bit of money before a solution was found. But before I get into that, let's just have a look at these switches. You've got here at the top two slide switches. Below that, a single push button switch. And over here there is a changeover single pole switch. It's effectively got two positions. And courtesy of Wikipedia, we have an exposed diagram of a micro switch, and that's equally simple, with a common wiper connection here, a normally closed connection here that runs down to that contact there, and a normally open contact here. Yes, they all look quite innocent, but they can all hide a problem. And it's a problem that a lot of people are familiar with and some people are not. And that is that they can be indecisive. They can't quite make up their mind what they want to be. And that can cause problems. In this particular application, it's a company that I knew, and this was their product. It's a fairly primitive diagram of a certain aspect of their product. First of all, we've got here a slowly rotating threaded shaft with a switch, mechanical switch actuator that would obviously slowly move up and down this shaft. And when it reached a point here, and this is a micro switch, this type of device here, and here's the actuator of that switch, which is this point here. I don't think the actual micro switch in this product had this lever attached to it. When this switch actuator impinged, reached this point of the micro switch would flip over, closing its normally open position. It effectively earthed or put 0 volts at this point here that actuated an inductive load. Now, I can't quite remember whether this was a DC motor inductive load or whether it was a solenoid coil, but it was quite heavily inductive. They had installed, this is the company, the manufacturing company, they had installed a back EMF diode here to squash any back EMF formed when this inductor was switched off. Anyway, so this product, although it wasn't a consumer product, they manufactured in ever increasing, slightly medium volume to industry. But the output of their product actually was a service or facility for the public. But every 3 months, approximately 4 months, an engineer had to be sent out to this equipment, and the micro switch had to be realigned because the position, the mechanical position of this shaft was critical. And incidentally, the whole of this equipment was in a semi-critical application. So it was very important. So the manufacturing company had to obviously pay for an engineer to realign this micro switch. Well, that wasn't the end of the problem, in that after perhaps about a year from new, the solenoid or motor here, this inductive load, would burn out prematurely. Well, what they did, naturally, they contacted the manufacturer of the motor or solenoid, and also the manufacturer of the micro switch they contacted to get their recommendations as to the components around. Well, obviously, as this is an inductive load, there's an arcing going on between effectively these 2 points here when the contact is eventually disengaged from that point back over to here. So the manufacturer of the micro switch recommended an anti-arcing capacitor here, which is C2, and the motor manufacturer recommended a specific diode for the back EMF, and also C1, a capacitor across their solenoid stroke motor. But although it felt as though it improved the situation a bit, the manufacturer, it didn't really solve the problem. And the manufacturer continued to send out an engineer and eventually replace this motor stroke solenoid. And of course, all the while kind of upsetting the customer. So they contacted me and presented me with the problem. And they also put my arm up my back because they didn't want me to create any form of radical change. They wanted to keep their production of this more or less the same. They also didn't want to make radical change because they submitted the whole of this machinery, this piece of equipment, to compliancing. And compliancing at today's money would cost at a minimum £10,000, and that can easily climb up to 50,000 grand if there are slight complications, and if there had to be additional alterations, there's additional costs. So they were very reluctant to make any change here. Well, of course, you can't solve a problem without making some change. But what they really wanted, ideally, is something slotted in between these two components that magically solve their problem. Well, I thought about it for a while, and I thought something was worth a shot. I kind of knew, I felt that it was something to do with the way this micro switch was being physically operated, maybe operated too slowly, or had some form of resonance in this mechanical shaft, and in some way was causing an oscillation on this point here that was stressing this inductor, the motor or the solenoid. And I came to a solution, and it solved the problem. I didn't know quite exactly the scientific explanation for the solution, but I was certainly very happy that my customer, the manufacturer of this, was very happy with the solution, and it didn't cause them any alteration to their product. Now, I'll go on to demonstrate the problem with all mechanical switches. And this piece of equipment is actually very dated. I'm talking about a long time ago, more or less when optic sensors were just coming to the fore in this type of application. And if you were to design this now, you'd probably have some sort of optic interrupter switch that would electronically drive this coil. But they hadn't implemented that, and this is going back when this type of configuration was actually quite common. But what was unique to their application is the slowness of this switch actuator. Anyway, I'll show you what can happen with switches when they're new and when they've aged a bit, and you can see effectively the size of the problem. And I'll go on to that demonstration now. Now here we are at the bench, and I've got this set up whereby I'm checking the waveform that the switch, when pressed, the single little push switch, when pressed, the waveform it produces. Now how I've generated this waveform is I've got a USB power bank here. I've got the power bank's filter. This is the subject of another video I've done, and I'll leave a description of that. And I've got a 6-volt battery source here, and here's this simple little DSO, and I've pushed the switch once. Here we are at the leading edge, producing a single bounce there. This is a new switch, so it's going to produce quite a clean image, and as the switch wears, this bouncing will get worse. So it's a kind of switch indecision, isn't it? Now the setup is the earth of the, or 0 volts negative of the battery goes to one side of the switch, the positive of the battery goes to one side of a 4K7 resistor, the other side of the 4K7 resistor goes through to the other side of the push switch, and the DSO goes literally across the switch itself, so that it's going from the positive to 0 volts or negative. And that's what you see on the waveform there. That's the +6 at the top there, and that is 0 volts at the bottom. So I'll operate this switch now. This does not produce bounce on every switch occasion, simply because this is a new switch. In fact, switch bounce only really occurs on a new switch, maybe 1 in 6 or 10 operations. So I'll now go to zooming in on the DSO so that you can get a closer look. So this is a close-up of the DSO scope and my switch, and I'll push it again, and that's the next one. You can see it's a perfectly clean signal, and again,
and again, and again, and again, and again. You can see that there is a bit of bounce going on at the rising edge there. Clean, 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 clean. And there we are. I don't know whether you can see that again on the rising edge. You've got a double switching action there.
There you are, and you can see what's going on here quite clearly, again on the rising edge. So this is when the switch is being lifted off. It's producing a double, a bit of, I suppose you could describe it as oscillation, but the switch contact is not being made completely purely. Now what I'll go to now, I managed to do a recording of a dirty switch, which will really surprise you. Now I recall that image. And there you have it. How about that? Now this is a very old switch with contacts that are relatively worn, and you can see it really is a myriad of spikes and whatnot. And as you can imagine, if that's driving an inductive load, that there is going to be consequences for this kind of waveform. We tend to think of a switch as operating in either on or off, but in reality this can be squirting out quite a high frequency here, and intermittent on and offs. Furthermore, if you have a digital system, of course, we're looking at possibly a 1 millisecond gap on the median in the area of here, and possibly 10 milliseconds gap there. Well, if you've got a CPU polling this switch to work out whether it's been pressed or not, and the polling is not inhibited in some way, you can see how the CPU, because in a gap like this of 10 milliseconds, a CPU could be running 10 million operations, a modern CPU. So if this switch is being constantly polled, how does the CPU know whether the switch is truly turned off from being turned on, or the other way around? Because there are so many noughts and ones, so many ons and offs here, that unless the CPU, unless you apply particular software conditioning, the CPU is going to go berserk. And this is what happens with fast electronics and switches, and that's the reason why we have anti-bounce circuits. But all software anti-bounce circuits have their limitations. So I'll move on to the solution that I created for this company. Well, here we are at the Falstead online simulator, and I've presented here my solution, and very simple it was. Basically, it's a cross-coupled Nand, but I've titled it as cross-coupled gate because you can use NOR gate or NAND gate. It depends on how you wish to implement this. But I chose a cross-coupled NAND. And at the top left here is the two gated cross-coupled NAND with the micro switch here, which was the micro switch on the shaft, actuated by the shaft actuator. And you've got normally open contact here, normally closed contact here. And I'll just go through this one in finer detail, but the other two implementations operate in a very similar way. First of all, we have the contact placed in a normally open position, the wiper of which is taken down to 0 volts. You've got two pull-up resistors here to a supply. It's stated here as 5 volts, but in actual fact I think the application ran at 12 volts. But as this is a CMOS package, it's well within its voltage supply range. So you've got two pull-up resistors. Now in the normally open position, you've effectively got 0 volts, and a lot of people understand this very well, but there are some people out there that probably don't quite understand how this works. But you've got 0 volts effectively put at that point there, and being a NAND gate, if any of the inputs are at 0 volts, the output is at a 1, and if that's at a 1 there, the 1 is presented at this gate here. Well, the other input to that NAND gate is pulled up and is not taken down to 0 volts, so you've effectively got a 1 there and a 1 there, the output of which then, because it's a NAND gate, is a 0, and the 0 is then transferred through to the other input of this NAND gate. So you can see this system is locked. Now if I operate the micro switch here like that, you can see that this cross-coupled NAND has completely flipped and in the same state as it was in the normal open position, but flipped. So you've effectively got 0 volts here, 0 volts at that point there, the NAND gate, so therefore it's a 1 on the output there. The 1 is driving this LED, which is the green LED, and I'll tell you about that in a second. So the 1 then gets transferred to the input of this NAND gate. There's a 1 there and there's a 1 there, so therefore that is at a 0. The 0 then gets transferred through to the input of there, and the system is now completely locked. The advantage of this, of course, is that you've only got one rise time and one fall time for an actuation of the micro switch, and so therefore it doesn't matter how this bounces on the contacts. It only produces, the output of this only produces one fall and one rise. The green LED, incidentally, is not really a green LED. In fact, in my application, this was actually a transistor-driven relay. And in fact, if my memory serves me correctly, the relay I used was a reed relay because the application only required a switch with 2 wires, which is in a normally open position, and when magnetized, the reed switch would close. Now, going back to the micro switch, and I will demonstrate this on the bench in a minute, but just to sort of illustrate slightly, let's get back to the start position here, and let's just illustrate how this, in a micro way, how this actually functions. So as the micro switch is actuated, the contact wiper here lifts from the surface of this. Well, the state is not changed in this cross-coupled NAND until, and it doesn't matter how that wiper bounces on this contact, this state of this flip-flop will not change until the wiper has made a first contact on the other side, and then it doesn't matter, and that will flip the NAND gates here, and it doesn't matter how many subsequent bounces occur on that contact, this will remain locked. It's actually, this wiper has just activated this flip on the very first contact it made. And then, of course, the reverse is true. And that is how this works. Okay, so let's move on now to the NOR gate implementation of this logic. And you first see that the difference here is subtle, in that instead of having pull up resistors, we've now got pull down resistors, and the wiper of the micro switch is now at +5. And so therefore, if we just go quickly through this logic, as that's at a +5 there, that puts that at a +5 there. The +5 there on a NOR gate means automatically that you have a naught on the output here. If there's a plus on either input here of the NOR gate, you will get a 0 there. The 0 there is transferred to the input of that NOR gate. The other input is pulled down through this resistor, so you have a naught there and a naught there, which will automatically, with a NOR gate, produce a 1 there. The 1 there fires up that LED, the 1 that is transferred through to the input of the other NOR gate, and now the system is locked. And if I operate the micro switch, again similar to the 2 NAND gate above, you will see that it flips over, and the green LED is a transistorized relay, as I mentioned before. So you've got that there. And I finally move on to what I called here a 2 times NORI NAND gate. And it's worth bearing in mind when you're designing with a discrete logic like this, it's good to have the truth table of the logic that you desire in your head. The actual implementation of the logic can be a varied number of gates. So in other words, providing that the logic is true, it doesn't really matter what gates you use. You can implement the logic that you require, sometimes out of spare inverters, a NOR gate or a NAND gate that you've got spare in other gates. So you don't necessarily have to implement another NAND gate chip on your board. You can sometimes make up this kind of simple logic out of spare gates and inverters. So this one, I've just done that. Now in my stock, I have the 4011, which is a 4 times NAND gate, but I don't have a NOR gate. But of course, I can make this up. So I could have implemented it like this, but in actual fact, I don't have the 4001, I think it is, that implements a NOR gate package. So I've made it up here out of the 4 gates of a single NAND gate. And effectively what you've got here is exactly the same as this twin NAND gate here, but I've inverted the inputs. I've effectively used the other 2 NAND gates as inverters, but this could be an inverter from another package. And as you can see, the input resistor to this inverter is a pull down implementation. That is a pull down implementation with the wiper being at a plus volts. So therefore the whole of this circuit is identical to the twin NOR gate cross couple implementation. And it works exactly the same way. And that's it. The next thing I'll do now is demonstrate this back on the bench. So here we are back on the bench, and we have in front of us the infamous DSO. It's battery power pack and a 6-volt lantern cell and a red LED and a green LED, and in the middle there the chip is the CD4011. As I said, I didn't have the 4001, which I could have used, but I preferred this simply because a double NAND gate gives you the option of having the wiper, as we've discussed, at 0 volts. You don't need a supply to orientate this flip-flop arrangement with 0 volts. If I were to use a 4001, I would have had to establish on the wiper a positive voltage, and that takes a moment or two to establish. And as this is in a semi-critical application, this flip-flop could have fallen into an unknown or undesirable state. Right, well, I get on to operating this. Well, you can see I've got my stylus here. Now this is actually wired as though it is the wiper of the micro switch, and in actual fact this stylus is a mechanical drill really, but I use it as a pointer. And you can see the signal on here, and that was from a previous switching of this. So the micro switch, when the mechanical shaft actuator was not touching the micro switch, the wiper would be on the normally open contact, and it doesn't matter how many times I'm pulsing onto this contact with the wiper, the state remains the same. Now when the mechanical actuator actually just starts to hit the micro switch, the wiper would move over quite rapidly. I'm moving it slowly over to the normally closed contact, and bang, it flips. And as you can see on the waveform there, the state of change is very clean. There are no additional pulses. And what I'll do, just to emphasize that, is I'll go back. So if the wiper is touching now the normally closed contact, it will take the micro switch to the wiper to completely move back over to the normally open contact and operate that before it resets the flip-flop. And there we are. That's basically how the operation. Now I do this quickly so that we can establish a complete on and off waveform on the DSO. So if I do that, there you go. And you can see on here that it is a very clean waveform. And if I adjust this, I can move the pulse that I just made around, and you can see there are no additional on or offs or transitions. It's completely clean, and this rise and fall time is actually quite sharp. So that was my solution, and I hope I've demonstrated that clearly. Let's just give it one more go for the sake of it, shall we? Let's go. So the wiper of the micro switch is resting on the normally open contact. It moves across as the mechanical actuator starts to apply pressure on the micro switch actuator, mechanical actuator, and eventually it touches the other contact, the normally closed contact. And then, doesn't matter how many times that's pulsed, it remains the same. And then when the mechanical actuator moves away from the micro switch, the micro switch wiper will change state to the normally open, and it can pulse there as much as it likes. So this would make a micro switch live a very long time, because the current going through the contacts is reduced to about, I would think, about 1 milliamp. You can adjust it to whatever you like, but I think 1 milliamp is what I chose here. And that means its life is extended. And of course, if the contacts become a little hairy with time, then because there is this flip-flop in in the circuit, this micro switch would have to wear considerably before it reaches its end of life. Now, what did I learn from this? First of all, if you design a piece of equipment, make sure it goes to the customer right. So kind of make something right first time. It wouldn't have been difficult for the manufacturer to have soak tested this for, let's say, a month or 2 months for the solenoid, the burnt out solenoid or motor, to have reared its head, and the realignment, the continued realignment of that micro switch, all that could have been ironed out before any units were sold. And that had the effect of upsetting customers and reducing sales. So it's important to get things right first time. The other thing, as electronics people, we do tend to love our complexity. It would have been so easy for me to have got them to change the micro switch to some sort of optic device going into, let's say, a microprocessor or a controller, with the additional complications of programming and cost and alterations, and that may have had a knock-on effect with the compliancy testing, etc., etc. But this was such a simple solution, and quite frankly, a 12-year-old could have designed it quite easily. I could have done that at 12. I started my interest in electronics at the age of 7. So I could have done this. This modification actually saved the company a considerable amount of money, but I have to say it established, it heralded a lot of kudos in my direction, and a lot of work was delivered to me on the back of this. So it did me a great favour. This simple solution did me a great favour with this company. And there we are. Enough said. I'll get off my soapbox now.
This is Beamer signing out for now.